All right, so let's start again. This morning we had an introduction to jamming, and so this afternoon, Jorge Kurchan from ESPCI will continue the discussion on jamming. So Jorge in particular has been thinking recently about the exact connection between the jamming and the glass transitions, which I believe will be part of what he will describe to you. All right.
Okay, thank you very much. So this, rather than an introduction, is going to be a pre-introduction because I'm going to go at a more elementary level than Bulbul's talk. So, so you've probably seen a few times, and you will see a few times more, this diagram. This is the jamming diagram. It was introduced by Liu and Nagel. So what you do is you have the axis, temperature, 1 over density, so that this is the high density limit. And here you put, for example, the shear stress. And what you say vaguely is, well, if I have a lot of particles, which could be a colloid, but it could also be granular matter or something, there are ways in which I can make it jam. One is lowering the temperature. Another one is making it more dense. And a third one is, if it's already jammed, I can unjam it by applying shear, and this will make it move, and then I'll force it to move. This might make it expand if the thing is at constant pressure. And anyway, this will unjam the system. So vaguely speaking, we all agree that jamming means there are several ways, including non-equilibrium ways, because the moment I start stressing the system, it will move, and then it will be out of equilibrium. Several ways in which a system jams. And the usual thermodynamical way is temperature and density. And then you say, well, there is this surface beyond which my system is jammed, meaning that it has become a solid. I still have to define for you what I understand by a solid, and I will in a second. But, so this is basically the basic idea. So this is a very attractive idea because it allows you to talk about several things more or less on the same footing. Now, the question is that you will see that when you zoom into this idea, you begin to see a lot of features that are not as simple as that. In any case, this surface is supposed to separate a solid from a non-solid or a flowing region. Okay, so the first objection you should immediately make to a diagram like this is that, you see, there's something inelegant here. I put temperature here, and I put density. So temperature is conjugate to energy, and density is conjugate to pressure. The quantity that would be nice to put if I put temperature here is pressure here, but the tradition is to put density and temperature. That's a matter, if you want, of symmetry, of elegance, or whatever. There's a more serious thing, that if I am shearing the system, then I no longer have a right to talk about temperature. I have a system in equilibrium, out of equilibrium, sorry. So when a system is out of equilibrium, I cannot define a temperature for it in principle. So what temperature am I talking about the moment I am on this axis? The answer is, well, probably, presumably, you're talking about the bath's temperature, which has a right to exist, but not of your system's temperature. And as a matter of fact, had I put pressure here, I wouldn't have a right to talk of the pressure of the system either. Okay, so, but that's, you know, matters of mostly elegance. So, okay, let's continue. So what do we understand by a solid? So this is a schematic picture of a crystal. Imagine that this would be a one-dimensional crystal. The particles are disposed close to, if you're not at zero temperature, not exactly in regular positions, but close to regular positions. They vibrate around, However, because they are essentially plus or minus an error in regular positions, when you do the Fourier transform, you can prove that this doesn't spoil the fact that there are going to be delta peaks. Omega here should be space, so this should more typically be called K. And you see these Bragg peaks. That's one way of looking at it. A different way of looking at it is to say that if you average over time the motion of these particles, they will vibrate. You will get, you take an average, you're going to get a continuous density profile, which is the average profile, and this profile breaks translational invariance. So it has features that stay put in time. The particles vibrate, but on average, time average, you still have a modulated density.
So okay, I assume you suppress the natural fluctuations given this one dimension well enough that you still get back.
Sure, this is actually, this should be a 3D drawing.
Innocent of the audience.
Yeah. It's not a 1D system even. It's, let's say, it's a schematic drawing of a 3D system. Yeah, absolutely. Another thing that I'm going to insist a little bit more about is that particles can exchange and will exchange, and it is not the fact that particles are ordered. Particles are not ordered. What is ordered is the density, the typical density. And I like to make the analogy with an army where a general has a name, but it will be substituted by another gentleman who was previously a soldier, but the order in the army keeps being the same. And although you do not have an order in the sense that Mr. Jones will be the only general in this army, Mr. Jones will die or will go away, will retire, but the places are the same. And in here, it's the same thing. So if you are going to follow particles by respecting their identities, you're going to surely miss the order, and this is not what you have to do. Okay, so please do stop me if you have questions. Okay, this is crystalline order, which is the one we understand better. So let me assume now that you have a liquid which you have supercooled. And so what do you see? What you see is, for example, imagine these particles. There's this configuration. Then via the vibrations, you go to this one, to this one. They are very similar. And you see a profile that, on average, an average density profile. This time, it's no longer periodic. It's amorphous. But it lasts for a long time. So I can take time averages over several windows, provided the time window is smaller than a time that I'm going to call the alpha relaxation time. I have an average density profile. In almost every respect, I can say the same things I said about the crystal a second ago. The only difference is that it is not periodic in space. And there's another difference, that there's not only one option, there are many. So all these three profiles belong to this other density distribution. So particles vibrate around their positions in such an exchange themselves and everything, in such a way that you do get some profile that lasts for some time. In the previous example of the crystal, order lasts forever. In this case, it lasts for some time, and then you move on to some other different average situation. And if you do the autocorrelation, which is, well, I haven't done it, but which is simply the product of this average rho over different times and integrated, what you see is that for a long time, you're very autocorrelated. This descent is just the vibration of the particles. And then you move away. So this is the typical time that it takes for an average profile, which was quite stationary, to move into another average profile, which is quite stationary too. The example of a crystal is exactly the same, with the only difference that this thing never falls, and it goes on, meaning that the alpha relaxation lasts forever, meaning that there's an average profile that stays forever. So now, if these modulations are really permanent, or in other words, if the density modulations really last forever, then I am just in the same situation as in a crystal, with the only difference that I don't have periodicity in space, and I will call that a solid. So a solid for me, or let's say a normal solid, is a solid where average density modulations stay there, and there's rapid vibrations, but once you average that times away, which are short times, the average modulation stays forever. Notice that this does not mean that the particles stay in their places. They exchange, but by a miracle, there is some conspiracy that makes the average modulation stay. So this is going to be the definition I'm going to adopt. You will see why. And I think it's the most robust definition of what is a solid. So, okay, this is just, so two elements to take into account: the definition of what is a solid and the fact that the alpha relaxation time to have a true solid, a real honest solid, has to be infinite. If it is not, I still cannot call that a solid because the thing is naturally flowing and not keeping its things. And this thing can be finite for several reasons, which could be that the temperature is too high, that the density is too low, or that I am shearing the system and it keeps it alive and this alpha relaxation doesn't manage to become infinite. So when I drew this phase diagram, the jamming diagram, the region that I call a solid or jammed is the region where T alpha, presumably this is what people mean, is infinite. Okay, so now one thing about the definition of the J point. So if we go back to this diagram, you've seen this already several times, but let me go through it again. There is a point here that is 0 temperature and 0 stress, which is supposed to be the first time the system becomes a true solid. So it's the least density at which the system jams and becomes a true solid. And Liu and Nagel have called this the J point for jamming. I'm going to, let's say a few things around this. There's a whole physics that is now being constructed around this point. There's a physics which is supposed to give some enlightening on the glass transition. I would like to comment on this, but there's quite a lot of literature on this, so it's worthwhile to elaborate a bit more. Okay, so so how do I define the J point in one inambiguous manner? So what I do is, in the computer, the easiest way, I mean, in the practical life, I could use a piston with hard spheres, crunch it until it jams, and stop there. In the computer, it's better to put your particles in some position, inflate them, put your particles in some position, inflate them a little bit. If there is really a little bit, an infinitesimal amount, if you create it as superposition, a tiny superposition, you avoid it by doing a minimal rearrangement, and you go on. So particles are inflating infinitesimally all the time, and elbow against elbow, they are pushing each other away. And you do this until you cannot do it anymore. There's a moment where nothing you do allows you to inflate further, and that point you call the J point. Now, Now, the J point has been shown, and I'm not going to talk a lot. Oh, something happened here. Shall I use here? No. Sorry? I did
movies, animations?
No, there's no movies. Talk about jamming. Okay. No, yeah, go back, please. Back. Okay. So this J point, which is the very first point where the system jams, has a lot of interesting properties. And you can show, and if I have free time left, I'm going to say something more. But you can see that what one can show, and this has been done a lot by the Chicago group, is to say that that point is critical in some sort of sense. Why is it critical? Because it is the very first moment at which the system jammed. So if something is just about jam, you remove one particle and the whole castle will have to rearrange, because it is just in the very first position where you had exactly what was necessary to first stop it. And because of this, it is critical because there's nothing redundant. The moment you perturb something, you make a terrible catastrophe, and then the system has to rearrange and find a new position. So for this reason, this system, this point is critical and has a few interesting properties. The question is this criticality what we were looking for when we try to understand the glass transition? So the ferromagnets have a critical point, and we think we learn a lot when we understand the critical point of a ferromagnet. With glasses, we may or may not want to find this transition. The question is this critical point which does exist the long searched for critical point of glasses? And I would say the answer is no, although it has a bearing for glasses, but we will see. Okay, so this is the procedure to create it. Now, let me go for a second back to the jamming diagram, and let me make an analogy between moving along this line, so changing the pressure and density, and moving along this line, which is changing temperature and energy. I want to convince you that they are very closely analogous. So, so that a lot of things that you know about an energy landscape, you can translate to this kind of situation where you're compressing, and you can more or less rewrite the same papers that have been written with this, in this new plane. So, so imagine this is a sketch of phase space. You have hard spheres. This here, the horizontal axis symbolizes all your coordinates. And this arrow here stands for the radius of the particles you're inflating. Notice that you're inflating them all at the same time, their own common radius. And of all the possible configuration at this level of radius, these ones are the ones where there are no overlap. This is a sketch. Now, what happens if I inflate the particles a little bit? Now the number of configurations that, so the radius is a little bit larger, the number of configurations that do not overlap is less necessarily, because if they were overlapping, they're still overlapping. If they were not, they either are not or they overlap. And if I do this further and further, these kind of configurations with no overlaps begin to be less and less. The set may become disjoint. You can easily construct an example and convince yourself that it does become disjoint. And you go on and on and on. At a certain point, the configurations that were close to this one disappear, but these ones are more lucky, until at a certain radius, poof, there are no more configurations at all, anywhere, such that there are no overlaps. And this is the optimal packing. So this is a radius. This is the whole phase space. And this is the allowed configurations at each radius. And now I can construct a kind of energy, let's say, which is the envelope of this curve. And what is this green line? It's just the first radius at which, for that configuration, keeping the configuration fixed, it's the first radius at which you get an overlap. So, and indeed, the optimal configuration now is a minimum of this green curve by construction. A basin of attraction is going to be a possibility of packing that will lead you to this local optimum. And you can do better. You can easily convince yourself that when you were doing this J-point procedure where you inflated infinitesimally and you moved infinitesimally, you were not doing anything else than this procedure. What you were doing, in fact, is moving you start in a configuration until there's a slight overlap. Because I cannot increase the radius with this slight overlap, I correct it, so I keep inside. I correct it, I keep inside, I correct it. So you see that this inflation process which defines the J-point, which is just a compression, is just simply, you can convince yourself easily that it's just following a gradient descent in this pseudo-energy landscape. Okay, so to recap, we have a system of hard particles of any shape. We are inflating them all at the same time. And in fact, if we are doing a procedure where they inflate infinitesimally and elbow one another so as to find their space, what you are doing is for this artificial construction that I made, It's exactly analogous to doing a gradient descent at zero temperature a zero temperature quench in a complex landscape. So this is, in other words, what you are calculating is what you would call an inherent structure. Yeah. Yeah. Okay. Yes. Sorry about this. This is I forgot to erase this from transparency, but it's an interesting thing to say. There are many problems where you don't want to have forbidden things and where you have to maximize something which is not the radius and optimize. The most famous and the most beautiful is when you have logical clauses which you add and you want to not generate contradictions. So you add more and more clauses, and the set of Boolean sentences that satisfy more and more clauses is necessarily less and less big. So the process of adding clauses, this is called the satisfiability problem. There comes a moment where if you add just one clause more, so that not 1 plus 2, then there's no more solutions. That's exactly analogous to inflating these particles, because it's making the non-forbidden thing, the constraints, more tough. And you could exactly use this analogy and, in fact, understand a lot of questions of the optimization program by using the analogy with an energy landscape. Okay? So this is the radius growing in this direction, but it could be the number of clauses, or if you're coloring a map, the number of colors you're using. Because the more colors, the less colors you use, the hardest it is to color a map with no two countries having contiguously the same color. Okay. Thank you for this. So once you understand that this landscape is very close to the landscape of an energy landscape, there's a few things that immediately become clear to you. One of them is that this J point, which is start from a random configuration and drop dead at zero temperature and go where this takes you, this, of course, cannot lead you to an optimal situation. I mean, nobody in his right mind will think that a quench to zero temperature will optimize a glass. You're not going to find this way the ground state of a glass. There's another thing you would not expect is that this level to which you get is going to be unique. Of course, if you start with more or less optimized configurations at this outset, you expect that your target configuration to which you go is going to be deeper. In fact, what you can do, can I use this blackboard or is this forbidden? I prefer on it. Nah. So, thank you. So there's thing that Shri did years ago with energy, which is you start the system in equilibrium at a given starting energy, and you drop dead at zero temperature and see to which energy this takes you. And what you find is that if the energy at which you started in equilibrium is very high, you go roughly to a very similar place. But there comes a time when you have started from an energy that is equilibrated at a rather low energy, where the target energy begins to be deeper, so that the preheating situation, pre-equilibration begins to be useful, and this is called a crossover or even his temperature. So now what you immediately see for no extra cost is that you can do exactly the same thing, given that here you start with the radius of the particle. You inflate, but this time you start in equilibrium, and you inflate until you go to the target situation in which you get the J point. And you can do exactly the same thing. Apparently this was done by Reichmann 4 or 5 years ago, but I don't know to what extent he was aware that he was doing exactly the same thing. But the point is that you see, one of the things this convinces you of immediately is that the J points to which you are getting have different target densities, depending on from where you start. So morals of this is that the J point is not unique. Should not be expected to be unique. A second thing is that you can easily invent a Monte Carlo program that will thermalize hard spheres. It's very easy. You use your yes, sorry. Yes. This is what they do, in fact. This is what you and Nagel implicitly do. They do start from what would be the analog of infinite temperature, so a completely random configuration. But the point is, you can find other target points by preheating the system or preconditioning the system. Only that. Sorry? Oh, sure. Also, starting from radius equal 1 is a unique procedure too. A little more dimensional, but okay. So another thing you can do easily is write a Monte Carlo program where your particles have a given radius. Remember that the analog of radius or volume of particle is the energy. So you propose a change in radius and you accept with the Monte Carlo rule. So immediately you realize that this can be done. And so on. Okay, so this is to say that the discussions that you see, and often people are not so aware of this, that the discussions you make on hard spheres, don't expect them to be very different from soft spheres. It's just that you have to look at the right variables. When you work at fixed radius, it's like working in microcanonical in a system with soft particles. That's all. Okay. So, moral number 1 is that this axis is not very different from this axis. It's just a matter of rethinking a little bit, and instead of controlling the temperature, you control your piston. But conceptually, there isn't an enormous difference. Number 2 concerns now shearing. Now, shearing is a much more courageous step because it takes us out of equilibrium. So the kind of things we might know here is much more reduced. So now the question is, and this sometimes a solid is defined not the way I did, but in a different way. I apply a shear stress, I stop, and I wait. Does this shear stress go away by rearrangement, or does it not? A typical example where you expect that a shear stress doesn't go away is a chair on which you're sitting. You're sitting, it sustains some stress, and you hope that this stress is not released, because if not, you fall. So, and the question is, will a rearrangement eventually release this stress? And the answer, oops, where is it? Oops. Where are we? Okay. And the answer is, a finite shear stress will always relax. And, oops. Okay. A finite shear stress will always relax, and the reason is very simple. Just a little parenthetical remark. If you have a ferromagnet or anything that has 2 phases, and the red phase has a free energy density that is higher, there is this nucleation argument that tells you that you can always grow a droplet of the good phase, and the worst point you will reach is when you pay a surface. You always pay a surface energy, but you gain a volume energy. When you do the exact balance of these 2 things, what you find out is that if the free energy densities are different, it is always a finite barrier to nucleate the good phase. So the morals of this is that it is impossible, if you have temperature, which allows you to jump barriers, it is impossible to have a stable, metastable phase that has a higher free energy density. This is absolutely general fact, and in particular it forbids you from having metastability in a ferromagnet when you apply a magnetic field, because then one of the phases picks up a free energy density, and so it will die out, and it forbids you a number of things. The argument here is the same, when you shear this thing, maybe you don't see it quite here, but this is supposed to show a crystal. There will be a distortion in the crystal, which will cost the crystal an extensive free energy density. And so it is always possible for the system to nucleate the unsheared phase, and the barrier for this is finite. So a stressed system at non-zero temperature will always release the strain. So if you're sitting on a chair at finite temperature, sooner or later, by activation, you're going to fall to the floor. This is, of course, thankfully, this doesn't happen at shortish times. It happens at extremely long times, but it has to be taken into account. So if you're really strict and you want to define a solid as something that will sustain stress forever, you can only have a solid at zero temperature, or eventually with long-range interaction or hard spheres or things like that. Okay. So, of our beautiful diagram, if we really insist on talking about solids as something that resists strain, we have lost completely this side of the picture. Of course, there will be here regions where the timescales are long, but there will be no regions at finite temperature and finite stress where the timescales are going to be infinite. So if infinite is the question, then, as a matter of principle, then there is no surface here.
Okay, question?
Yes.
So, couple of questions, but
yes.
Answer when you please. So, I mean, this could also apply to the temperature density plane, what you just said, right?
You mean that temperature could destroy? No, because when you apply temperature, you're not benefiting some other phase. No? You can still have order at finite temperature if you don't have any shear. But it applies in a lot of cases that are very famous. For example, a superconductor carrying finite amount of current is twisted. The order parameter is twisted, and it can always untwist by activation. And this is why superconductivity, this has been long known, is metastable. And superfluidity is of the same kind, and elasticity, this was discussed by Sedna, is also metastable, because if you pull from something, you can always activate a hole in principle. So a lot of things that we take for granted of real life are only mean field approximations as concepts.
So the other question is, I mean, this diagram assumes that you always have, I guess, shear thinning systems.
Yes, yes.
Right?
This I should have said. This I took for granted at the very beginning. Right. I am assuming that when you're moving in that direction, which is not necessarily the case. Oops, I think I made a disaster again. Yeah.
I don't know how that works.
If you touch the wrong thing, sorry.
You might want to play it safe and use the keyboard.
Yeah, I'm going to do that. Okay, so yes, shear thickening exists. It's rare, but it exists. There are systems that when you shear them, no, but it doesn't work now. It has to be redone, and I will use it then.
But let me complete the question.
Please.
I mean, this is, no, so is this kind of a non-uniqueness, is there some, I mean, you also mentioned earlier that when you, as soon as you're shearing, the system is not in equilibrium.
Yes.
So they're sort of, are these two factors in any way related, or possibly related, that on the one hand there is a, maybe not, but the non-unique relationship, meaning on the axis, depending on the system you're looking at, you should either have the stress or the inverse of the stress.
You're meaning between the thing of the nucleation and the shear thickening. This could be true if you have some metastable thing under stress that it will always have to nucleate, yes. By the way, I decided to discuss only shear thinning, so things that become more liquid-like when you go in that direction, but you also have things that become more solid-like when you heat them, and this is called reentrance. But they are rare phenomena. In fact, shear thickening is very close to reentrance, I think. Yes, indeed. So this brings me to my next thing, which is, as I will say now, that the J point is not unique. It depends on how you started the system. And when you're talking about the physics of this point, there are several of those, of different densities. And this has been showed explicitly in simulations by these people. But let me give you an example that I think has to convince you. Because people are not particularly convinced about this. They think that, yes, you go to different densities, but this goes like the square root of the 1 over square root of the volume. I am claiming that you go to really different densities. And you can convince yourself in this way. Take a system that is bidisperse, and it's a gas, and crunch it at infinite velocity. You're going to find a J point. Now, the proportion of big and small particles is going to be roughly Poissonian, random, because you crunched it so fast that there wasn't any rearrangement, serious rearrangement going on of big and small particles. However, you know that if you do a slightly slower annealing, to create a nice packing, you need to mix the big and the small in a rather homogeneous way. You know this, I mean, because putting many bigs on many small is not a good thing if the spheres are the right size. So you can easily be convinced in this case, at least in the bidisperse case, that it's extremely reasonable, and these people have shown it explicitly, that the J point to which you go depend seriously on the procedure. Seriously meaning order 1 in the density. Okay, so with these caveats, the diagram is a bit less as it was. You can still have, and there's no in principle reason why not, a line, not on this side, but a line here where you have a glass transition. You have the lowest of all your J points because it's the lowest because it's at 0 temperature, the ideal glass point. It's a ground state of the system. So it is a J point and it is a ground state. And then this line might or might not. This is the question of whether the glass transition, ideal glass transition exists or some form of glass transition exists. And you have a line until finite temperature. So this is the most, if we're talking of infinite times, the region where some modulation of density can stay permanently, it would be, if such a transition exists, along this plane and along this little sector. Okay, so, yeah. This one?
No, the zero temperature? Zero temperature plane?
This one?
Yes.
No. So if you are at 0 temperature and you apply stress, you could, again, this is still not very clear because you can still have nucleation at epsilon temperature just because particles make way for other particles. This would be nucleations in density, let's say, where you create a region of low density. But that's less clear, so you might have something there. Yes, but I'm going to come to this. Sorry, yeah.
Can you repeat why you consider this to be a sharp line? I mean, after
No. I'm saying at best we have that sharp line. Maybe not. This one, the red one, you mean? No.
Yeah.
I'm saying at the very best we might have that. There is no in principle reason why we should not. There might exist a phase transition that exists at finite temperature and at some density.
But it's not any more sharp than the one you just lost.
No, this one
There's
might be sharp, just like crystallization exists and is sharp, or a ferromagnetic transition, or this could be very analogous to temperature magnetic field in a ferromagnet. Sharp in the sense that you have some non-analyticity in your equilibrium functions.
Because you can have activation processes here just like you have activation processes that will make me fall to the floor.
Yes, I'm going to come to this. Can you repose the question if you're not satisfied in 5 minutes? Because I'm going to show 2 transparencies that are supposed to address that, but if you're not happy with the answer, ask it again, please.
Okay, one more short question. If you had a purely hot sphere system, then in any case your temperature axis is meaningless.
If you, sorry?
If you had a purely hot sphere system,
Yes.
then
If you have a purely hard sphere system, then the axis is meaningless with a caveat. So it is meaningless in the sense that the dependence on temperature is trivial. But still, hard spheres at any non-strictly zero temperature can make us an entropic solid. This is because the particles don't touch, but they every now and then crash against one another. So to the extent that the temperature is not literally zero, in which case the only possibility is to pile them, then you can have an entropic solid. And you can make the argument. Oh, okay. So no, I'm not taking any position on this. Random close packing, as in the way the Chicago group saw it, was the J point according to their procedure. But I have a problem because I have many J points now. So what can I say? Nothing. I mean, I suppose that all this is related to the procedure you use, and I don't think that you can escape that. The only thing you know is that there will be an optimal packing, for certain. There's going to be something that is better than anything else, but that's not the one you access with a quick quench, for sure. So, sorry? Yes. Yeah. No, I don't think so, because I cannot believe that a quick quench will take you there. It would be like thinking that in a temperature quench, fast temperature quench. Oh, okay, okay. Then you would have to say that what you do in ordinary life is not quite that. Yeah. That could be a good, yeah. Yes, so that point of which you would like to call random component is where the gas transition would be, yes. For hard spheres, yes. At zero temperature would be there, yes. So, sure. To avoid confusion, Zamponi and Parisi in their review invented a new word, just not to, because it's very extremely tricky to the terminology. Okay, so this line is the line that presumably might exist. So now I'm going to try to say something about two forms of solidity, and this addresses the question of why activated processes do not destroy a solid, may not destroy a solid, and you might still have a solid in the presence of activated process. It is not forbidden to have a solid even if each particle can activate its way.
I think you just wrote that that's a glass transition line, but we're used to thinking of the glass transition line.
Sorry?
You wrote that's a glass transition line?
I said that this is the putative glass transition line, yes,
but,
meaning that I don't know if it exists.
But
yes.
we're used to thinking of that in terms of a finite time scale.
No, this would be the one you would really get with an infinite time scale. If there is one, you really get with an infinite time scale.
Okay.
So this is
more
the
of like
ideal.
a Kautzmann temperature.
Sorry, the Kautzmann temperature as a function of the density, yes. That's yet another. Okay. You're right. You're perfectly right. But here, there's two answers to this. One is to say, okay, yes, you're right, but I assume that between the time scale of a crystal and the time scale of the optimal amorphous thing I can do, there is an enormous gap as compared to all the other times to get to there. One time is immense, the other one is immense squared, let's say. That's answer number one. Answer number two is, just to fix our ideas, we can think of a dimension, maybe in 342 dimensions, some group theorists, and there are, thinks that there isn't a crystal. We will never know. I mean, not in this reincarnation, in any case. And the other answer is maybe there is a mixture of sizes which does not have a crystal. We will never know, but it's true. Or, to give something closer to your heart, in a curved space. Yeah.
Binary mixture, which was somehow mixing more homogeneously. I mean, if you submit your paper about the J-point saying, look at this example with the binary mixture, it's completely random, or I do more order in how I put the particles, then the referee immediately will say, oh, but you're pushing the density of the J-point because you're increasing the order.
And I would say...
That's the Torquato sort of argument that...
this is what the referee...
Since you increase the order, you're shifting the J-point. So do you make a distinction between the crystal and I don't know, any types of order? Is the crystal special?
Yes. In any case, any amorphous system has a form of order. In any case, what I'm saying is that it's not crystalline order. There is a hidden form of order in an amorphous system that becomes more solid. But I would say, no, there isn't an order parameter that is as naive as the Fourier transform or the something silly that will detect crystallinity. I would say to the referee, no, this doesn't have more order in the sense that he intends, that a usual crystal is growing. There isn't any evidence of crystallites growing inside an amorphous matrix. Okay. In any case, if he really insists on this, the other possibility that you can answer is, okay, but the one you liked best, the one you created with your crunch, is not the topmost. I can make even more disorder than yours by doing strange things or very slow. So even yours is not good enough. So this could be the other answer. Okay. So about solidity. And now this is a distinction that is important. I know that several of the lecturers went on this, and let me insist with a slightly different point of view, but it's the same thing about the question of cooperativity and how do you get a solid. So there are two ways of getting a solid. One is a, let's say, more or less trivial way, which you can do without much mystery. And the best example of the more or less trivial way is this one, 2 coins in a matchbook. It has been shown by Rob, I think. Giulio and I used it in a paper, but we stole it from somebody else. From? Who in turn did it from Ruel, I think. So, so these 2 coins cannot be rearranged because they are hard, but there's nothing mysterious or thermodynamic here. There are only 2 of them. This is a solid in the sense that you cannot reshuffle the coins just because the constituent elements are solid themselves, not because there is anything subtle going on. This other example is the same. This is one-dimensional solid in the sense that, you know, you can make it. But it resists, but any activation, to go to your question, will kill this solid. Because it's not a real honest solid that is made by cooperativity. It will die if this coin has a finite probability of jumping, and any activation rate between any of these 2 coins will kill this 1D solid. But you can have solids that are not like that, and this is one of the most, I think, beautiful things that happens when you learn physics, and I think it's one of the most beautiful things there are. You can have perfectly soft particles with a potential like this, which can very or quite easily jump on top of one another at finite temperature and will do that. And however, these exchanges of identity, this is Mr. Jones becoming general from soldier and being promoted and so on that I was saying at the beginning, the average order persists and persists forever in spite of activation. The condition to do this is, I think, a completely miraculous fact. You are using things that are locally soft everywhere, and by a mystery of cooperativity, they create a solid out of nothing. And this is an essentially collective phenomenon because the only reason why you resist temperature is that the system has to be infinite. If the system is finite, then it won't work, it won't be a true solid, and with these rearrangements, it will suffice to destroy order. So this is a bit of a miracle, but believe me, it happens. And one way to convince yourself is just to calculate the minimum of this function, the one where you put all particles with this potential together, and even calculating the minimum and seeing the barrier to move away, you realize that the barrier scales with the size of the system. And why does it scale in spite of the fact that every individual thing is not finding any difficulty in moving and indeed will diffuse away? And it's because if you really want to destroy this, you need to do things like this. This is a very bad example, but it's an example, where you're shifting all this thing and you see I have to create an infinite number of superpositions in order to sort of break this thing. So this is perhaps not the most good example of how a solid is destroyed, but just to say that there is this miraculous fact that completely things that are completely soft can create something that is hard. This is the answer I was trying to intend to your question. Yeah. Yes. That's the other, yes, and it's very important, the remark. I used to have a transparency to illustrate what she is saying. There are cases where it is not only the energy to go that becomes infinite, but it is the fact that you can do it with finite energy, but you need to have a number of predetermined moves whose probability is 0, again, in the thermodynamic limit. This is what you would call an entropic barrier. So now the question is, what is the nature of the glass transition? For a crystal, there is little doubt. You can perfectly well have a crystal where particles don't touch. The radii are such that they touch once in a while, but they are not sitting on top of one another. So the question is, do we believe that the glass transition is like jamming? Because jamming is at the very least something like this, where things are just sitting on top of one another, but you don't need anything collective and you don't need anything mysterious. It's just things don't letting the other ones pass because each constituent is hard. This is a form of jamming which is, let me say, in a way trivial, although it's interesting from many points of view, but it's trivial in the sense that it doesn't require any cooperativity. This one does, and this one, so now is the presumable order in a glass of this kind or not? Well, we don't know, but people who believe, and this is the big deal about believing or not that glasses have a transition at finite temperature, or more precisely, believing or not that the time scale is something faster than Arrhenius. If you have a system like this, you can only have Arrhenius because you destroy the solid by simple activation of a few guys. But if you have a system like this, you will always have either a finite temperature transition or even a temperature equals 0, but with a law like the one Rob used, which is super Arrhenius. It's not just simple activation, you need much longer time scales as you approach 0 temperature. So this is the big deal about being Arrhenius or not being Arrhenius. It's a question of whether the glass transition is a conspiracy of a lot of particles, but then again, if it is, you have to accept that it's not an order we know. So it's more like an army, it's like a secret society where somebody has a higher level than somebody, but you are not told what is the hierarchy within the secret society, but there is one. And again, it doesn't depend on who is in which position, just like in an army, only that you have not access to the rules of that specific army. That would be the example of a glass with cooperativity. Shear doesn't apply, and in this sense, it is quite remarkable that shear is very different from temperature, true. Shear is destroyed by activation, but temperature is not. It's quite surprising, yes. I think it has to do with the nature of equilibrium that you don't have in shear. But I thought about it, but I don't have quite an elegant answer. Okay, so these would be, let me exemplify quickly the two ways. So this would be an ideal glass scenario. If you do a quick quench, you go to the J point, the original one. If you do a slower quench, this is 1 over pressure against 1 over the density, but it could be energy against temperature. You go to, I claim, a deeper J point, and so on and so forth. And as in all glass books, they tell you that if you could go infinitely slowly, maybe there is a singularity here and you have an ideal glass transition, maybe. And this would be the Kauzmann, in my case pressure, but it could be temperature. So if a glass transition exists, if a collective thermodynamic, etc., glass transition exists with cooperativity and a diverging length, then it would be here. And these are the J points. This is the deepest one, the one that Chandan would prefer to call the random close packing. The crystal I haven't drawn for obvious reason, but it would be deeper down. And so these are the J points. All of them are amorphous, isostatic, and with all the properties that J points are supposed to have. this would be the region where the glass, true ideal glass phase exists, and this would be a place where there is an infinite cooperativity length, because otherwise you cannot have a solid. And they are two distinct things, and they overlap in this point, which is the ground state of the ideal glass and the deepest of all J points. Now, that this point exists as a transition, I don't know, we don't know, nobody knows. Maybe yes, maybe not, because in fact what we can do in real life is something like this, and nothing more than that, even for a realistic system. So this is it. So, okay, final word. What can you do with this diagram now? Of course, chairs exist, one sits on top of them without much fear of falling. So what happens is that one has to talk about timescales. So what one could do is draw iso timescale surfaces. So this is the surface of things that have an alpha relaxation time of 1 hour. There will be another surface. The J points are somewhere here. There are some that are deeper and some that are not, because this point will take a lot to relax, but this point here will take less. So that seems okay, but it's not quite okay, because again, you have a time scale, but you have to tell me also not only the temperature of the bath, the density of the system, and the shear rate, stress, but you also have to tell me what is a process. If the process is stationary and you say this has been going on forever, okay, then you have a unique thing with a time scale. But when you have a glass like the ones you have, you don't have a stationary process. So on top of all this, the time scale depends on the history, because you have aging. And this is what I'm going to talk, but I think Greg is going to talk before me, and Silvio at the same time, more or less. So aging means that my actual time scale not only depends on where I am in this diagram, but also on the history of how far ago, how long ago it took me to get to that point. So the best you can say about this diagram is that you can use it with not, notice that I added, there were inverted commas in phase, now there is also inverted commas in diagram, because there isn't now, it's no longer a line that divides a solid from a non-solid, it's something that has to do with equal time scales, but this is even, remember that this is not even enough, because typically in glassy systems, it's also the history that depends. So 2 points that have the same values of these 3 things may have very different time scales. So you cannot even draw the lines. Okay, so the notion of jamming diagram, just like jokes and things like that, when you analyze it too much, loses much of its charm. But it helps to at least say that, yes, when things are dense and when you don't shear them much, they tend to be more slow in moving. Thank you. Exactly. Exactly. They ask too much questions. It's like people who want you to explain them the jokes.
An imposed static shear stress, isn't a solid anymore in some sense. You will still agree, though, that if you plotted stress versus shear rate, then in the thermodynamic limit, if something is a real solid, this curve has an infinite slope at zero shear rate.
It has a non-analyticity,
Yeah,
just like a magnetic field does.
Right, yes. So, I mean, you're not disputing that.
No.
Okay, fine. I just was worrying.
And there is the possibility, which we are trying to figure out with Giulio, by analogy with the magnetic case, that if you apply an alternate shear, there is a frequency at which you get a transition to something that doesn't disorder. It seems, but it's not, it's to be done.
Yeah, just one thing that I would like to, get clarified. There are these theoretical calculations by Zamponi, Parisi, Mezar, etc., where it's predicted that there is a glass transition at a density which is not the random close packing, which is lower than the random close packing. So I was just trying to understand how that differs from what you are saying here.
So I think that what Zamponi did is well, I'm sure he conducted a kind of poll on all his friends,
yes,
asking how should I call such and such a point, because he didn't want to commit to names that had already a connotation like random close packing. And I think that in the end, I don't know which one, if anything, he called random close packing. I'm not sure. The fact is, what they get, I can tell you what they get, but not, sorry? The glass close packing he did in order not to use the random close packing. Now, because he gets an ideal glass point, they would have gotten, had they done things in another way, a dynamic glass point. But all this is mean field, so, you know, you would get that. It doesn't prove anything with respect to real life. The values they get for the ideal glass phase, I think, are not very far. In any case, for monodispersed spheres, my impression is that when people say 0.64, they should give 2 decimals more in order to make conversation, because everything for bidispersed, no, and I think that she and Ludovic and showed this very clearly, but for monodispersed, everything seems to be so close, no? That maybe everything is played in the not even 1%. So this one, my belief, well, so this line, we are now convinced that they would be, except perhaps for the very last point, I don't know, but they would be all isostatic. The initial belief was that no, because for different reasons that come from models and other things, there is a line here that is something analogous to marginal, which this comes from the dynamics and other stories of spin glasses. So the expectation at the beginning was that only the topmost, the most rapid would be the only isostatic. And then upon better thought and constructing a model that did everything and could be solved, it seems that all of them are isostatic for the reasons that are usually given. So they all have roughly the same properties, and all the properties that we have studied so well apply or would apply to all of them, except that they're very different and have different densities.
Could you repeat once again the explanation why a solid doesn't exist at the 0 temperature plane?
At the 0 temperature plane, did I say anything? Okay. Okay, so no, what I'm saying is that, but this is going to be more hand-waving. If you have finite pressure, but 0 temperature, or let's say epsilon temperature, so the particles move but very, very slowly, or you have an equilibrium measure at 0 temperature if you want, at finite pressure, then I think that you can make nucleation arguments, but they are more subtle because it's not a matter of, you know, jumping in energy and falling, because you don't have energies you have. But still, people believe, I think, Giulio, you proved something, no? But you didn't write it, or that you could make space at finite pressure, but maybe you can comment on that.
Any configuration to any other configuration with a number of moves, which, I mean, well, the proof was that there are always finite barriers, so you can always move, so it takes some time, but you're going to do it. So if you can show, well, so you can use nucleation argument.
At finite pressure. It's only at infinite pressure and 0 temperature that you use the other kind of solidity. But if you are at finite temperature, non-zero temperature, and non-infinite pressure, the expectation is that you need something collective. If not, you're not going to have a solid.
other questions? If not, let's thank Jorge for a wonderful presentation. Kept us all awake.